Thank you, everybody, for joining today's ELISA Seminar talk. Today, we're very delighted to have Florian Gilcher to give us a talk on Ferrocene. It's a tool that qualifies the Rust compiler out in the open. Florian Gilcher is a managing director at Ferrous Systems. So I just want to give a quick introduction, and I'm going to pass the baton to Florian.
Thank you. Yeah. As said in the introduction, I'm going to talk about a Ferrocene, our project to qualify the Rust compiler to high safety as an open source product. I intend this talk to be around half an hour and then a lot of Q&A. So please take notes for questions. I enjoy the Q&A and would love a good seminar out of this. So quick thing about me. Hello, I'm Florian. I've been doing Rust since 2013. I've been a Rust trainer since about 2015. I've been part of the core and the community team of the Rust project until 2021. And I'm also a co-founder of the Rust Foundation, where I had my tenure until 2021 as well. I left because Rust is so big now that it's better to just care for one organization than three at one time. And that one organization, Ferrous Systems. Ferrous Systems is created in 2018, and it is nowadays mostly an open source maintainer company. We would like to frame us as with a team of 20-25 awesome people. Just for a quick overview of what we do, the most interesting for this group here is the left side, the open source one. If you have ever used Rust, you've probably used some of our software, particularly with the maintainers of Rust Analyzer. We've been maintaining parts of BindGen, Rust, re-implementation of sudo, and all of these kind of things. So we built fundamental parts of the Rust ecosystem. And we had this 2-year project to go into that, which is Ferrocene, which is a qualification of the Rust compiler that started in 2021 with a pre-assessment phase to see if it's even possible to qualify the Rust compiler for high safety, an execution phase of about 1.5 to 2 years, which mainly was the work that I'm now going to describe, and also describe the approaches that we took. And we have actually reached qualification last year. And we're currently in the refinement phase, so things building on top of the things that we'll be talking about in this session. So what is Ferrocene? It is a Rust compiler qualified for critical settings, and it's also meant as a reusable toolchain. So we qualify the Rust compiler as a downstream of Rust/Rust, Rust/Rust being the main Rust repository, which contains all the Rust tools, not only the compiler, but also things like Cargo, the build manager, Clippy, the Rust linter, and all of those things. And particularly when we're talking about Ferrocene, it is an application of something that the Rust project does, which is called the not rocket science rule of software quality to software qualification and certification. And the rule is as simple as it sounds: automatically maintain a repository of code that always passes all the tests. Sounds easy. It's actually quite substantial to actually make that happen. And I'm going to go into the details of that. So why do we want to use Rust in critical settings? Rust is a programming language that eliminates whole classes of bugs, particularly around memory safety, statically, while it has a runtime footprint similar to C and C++. So it has a lot of desirable properties of C and C++. It itself has a culture of correctness, but there's something missing: necessary certifications and quality management around the compiler, structured quality management. And the big question that I'd like to frame for the sake of this talk: can we take a huge open source project? The Rust compiler has around 250,000 commits and is quite substantial and qualified for safety. This huge question: can we work with open source in safety? So what do we need for qualification? First of all, we need the tool to be qualified itself, which in this case is the compiler. We need a covering requirements list, which in the case of a programming language is a language specification. what is the compiler even doing? What is the thing that it understands? What can I feed into it, and what can I expect to get out? Then we need a set of evidence that shows that the requirements are met, which are tests mapped to the specification and the test's output, and evidence of development processes that keep these requirements met. So how do I make sure that I don't lose track of them the moment that software is being changed? And that's actually a substantial and huge part of that, because as I mentioned before, we're a downstream of the Rust compiler. So we need to make sure that if there's a patch going in to rustlang/rust, how can we make sure that we don't lose track immediately? And this used to be a huge problem in compiler qualification itself, and led to a lot of compilers just be forked and then never updated. That has worked. As of October 30th, 2023, Ferrocene, based on the Rust version 168, has a certificate by TÜV Süd, and the certificate for 176, that's actually news from yesterday, is currently outstanding, which is our, so we're waiting for actually the certificate being delivered by mail. But the interesting thing here is we did that with full functionality. So Ferrocene is not a subset of the Rust programming language. So we have nothing going on like rustc to make the deployment of the language safe. We qualified the whole set of the language. It is, however, a compiler that's built, and it's an unmodified compiler. It is built in a different mode though. So we are changing some switches in the compiler to have it catch more bugs. For example, we are running with LLVM assertions, which makes the compiler a little bit slower. And in very niche cases that are actually interesting, crash. And because of the way how we produce it, we can actually ship all versions of the Rust compiler. We're qualifying some of them, some not, but we can basically qualify any version of the Rust compiler on request at a short notice. And that allows us a number of use cases that are not covered by upstream, particularly functional safety, long-term support, and all of these things. Now, there's a couple of interesting findings that came out of this. First of all, we found out that when we talk about testing, the Rust compiler in and by itself is tested to a very high degree already. And I always joke that qualification is a little bit of the process of going from gut feeling to actual tangible evidence that something is true. So we had a good impression that, and having a good and covering test suite of the Rust compiler, it was always a goal of the Rust project. We were just never sure on how to actually make the case. The other thing is, we found that the Rust project's processes are actually quite fitting for a high assurance and safety critical mindset. And we found, I mentioned that before, that we did not need to diverge from the main Rust compiler and its test suites. We had to add a few things though, which we have convinced the Rust project to actually add. So it's not like there were no changes made, but we made the changes in our main compiler instead of doing them in our branch. So Ferrocene is fully open source. You can go to github.com/ferrocene/ferrocene and look at everything that I'm describing actually happening. And we do have all of that, as I said, publicly available. In GitHub, you can look at the documentation that I'm describing here by going to public-docs.ferrocene.dev/main, and you'll get all the documentation for the current main branch. And you can look at our blog for updates, other things. Everything that we do happens somewhere out there. So big question, why have we chosen to actually go the route of why are we building an open source safety compiler? First of all, well, there is currently a new move towards open source in all kinds of vehicle industries. We've seen the Sophie, we've seen Covesa, the Eclipse SDV, ELISA, we're here. There's now an open source safety critical RTOS, ThreadX. And one of the things that we've been hearing quite a bit is it actually becomes a little bit problematic once you have open source software, that if you actually want to build it in a safe considered way, you still need to rely on closed source software that you get from somewhere. And the other thing is relationships. We have the same licensing as the Rust project. So it makes the question of, can we put something into the Rust project's code base, at least in the legal and in the licensing sense, very easy. Just need to convince the project that that change makes sense. Still a lot of labor, but at least we're talking. We find that the companies we're talking to want to get way more flexible and creative around their own tooling, which means they want to self-manage their tool chain. So it's also useful that we can say, hey, we can ship you in binary, but we can also ship you in source if you want. And our customer relationships, I mentioned, we're considering ourselves a maintainer company, become more and more a maintainer-user relationship, rather than hey, okay, you pay your license once and you get a binary ship relationship. People are interested in, yeah, we'd like to rebuild the compiler, but we also don't want to do all the work all the time. So when we're talking about project contributions, I won't go through all of them. This whole project actually had quite a few. Here's a small trophy list. Particularly, we are, for example, the first people who have ever built the Rust compiler on bare metal targets. And you see here fixed tests on panic abort bare metal targets. Why do we know that we are the only ones that have ever run this? Well, because there was quite some amount of things to fix to actually get the test harness running there. And as you may have seen, our main qualification is currently on ARM, other targets coming. We have already found a few issues on the ARM targets. However, the good news is Rust is very well trodden on ARM, so the quality is pretty high. The more we move into targets where Rust is not used that much, we find more and more issues. So that's also good news. The effort is actually worth something, either by giving higher trust in, hey, we can use Rust on ARM and x86 just safely, or identifying gaps on other targets that we still need to fix. And when I'm talking about using, having an open source implementation of this, this also means we are only using open source tools for that. However, not that many. I'll get into that and why that is later. Particularly, we use reuse by the Free Software Foundation in Germany, Free Software Foundation Europe, which is a license checking tool and making sure that all of our licensing everywhere is accounted for. That has also moved upstream to use it in the upstream compiler. We use Sphinx for documentation. We use Sigstore to digitally sign our documents because all of our assurance documents need to be signed. And we do that cryptographically by using Sigstore. We use a process automation bot called BorsNG, and I'll talk quite a bit about what BorsNG does. There's a star on this, which is this project is now discontinued, so we're maintaining our own fork. The reason being that for pretty low-key use of Bors, nowadays, a lot of the platforms, GitHub and GitLab, have their own implementation of this. So BorsNG has actually decided to stop maintaining that as a project. But our use is pretty advanced, so we're stuck in this unfortunate situation. We use a tool for releasing, Cargodist by Axo, and a lot of Python and Bash because, well, is there software without Python and Bash? Now, to get more into how did we actually pull this off? The first thing we do whenever we downstream something from the Rust project is we take great care that we don't modify any of the files that the Rust project has or any of the folders. Everything that we have is compartmentalized into other folders. Particularly, we only add to the Rust compiler. We never delete if possible. That also means that every night when we import the Rust changes, that also means that not a lot of things break, and particularly there's no collision. So we're extremely collision avoidant. So there's a lot of how to deal with Git around this. Additions are, however, substantial. We're talking about around 5,000 file changes and up to 70,000 additions. So the first thing that we add is additional documentation, a user manual, particularly for operating Ferrocene in a qualified environment. What are you allowed to do? What are you not allowed to do? And particularly a safety manual. Which are the parts that we looked at? How do you properly deploy it? How do you, for example, invoke the linker correctly? Or what are even the things you're allowed to do? What are the things you're not allowed to do? And where are there interesting, dangerous bits? So, for example, it documents what options you're allowed to pass into the tool. And for example, one of those options, number 3, uses shall pass command line option LLVM args protect from escaped allocs true, is a mitigation against a known bad interaction between the Rust compiler and the LLVM, which is an option for the paranoid, but as we're talking safety critical, we are paranoid. This fixes a bug that is extremely hard to actually trigger, but we still want to fix it. So let's talk about the process landscape. The most important thing is the Ferrocene process is an extension of the Rust process, and I'll get back to why that is important later. So first of all, what we do is we set a plan in our documentation. Hey, here's how we evaluate the Rust compiler, and that's how we evaluated it. And a report out of that. The evaluation plan is essentially we had a look at the compiler and how it works architecturally. The Rust compiler, for example, uses the LLVM and invokes the system linker. And on all of those bits, we could introduce errors. And the evaluation report coming out of it is evaluating all the hazardous events that can happen on the compiler and set any amount of countermeasures in order to mitigate those hazards. And then we have a qualification plan. The qualification plan are all the activities we do to counter those potential hazards. Particularly, we have got a certification for ISO 26262 and IEC 61508, so automotive and industry. So the qualification plan also lists how those activities actually address the activities required in those standards. What comes out of it is a semi-automatically generated document, the qualification report, how Ferrocene is qualified, and particularly including all the test output. For a final qualification, when we go into TÜV, this is digitally signed by the people responsible in our company, that these are the things that we actually did, and this is the documentation that fits the artifact. The interesting thing here is these documents are part of the main repository, so they are, in our case, considered part of the software. So the documents not building or the documents changing while being signed is actually something that makes our builds fail. And I go back to why that is important later. So I spoke about that we need requirements. And if you've been a little bit around Rust, you may have noticed Rust doesn't have a language specification yet. There's currently work on creating one. It's unclear when it's actually going to be finished. So we created our own. One note, it is important that that language specification is not something that's fit for creating a second compiler, for example. It only describes things that are very user visible and does not go into, for example, exact behavior of the reference checking that the Rust project has. One thing that's interesting about our spec is, and that's useful in our process, we made sure that each part of the spec is actually addressable. So this is section 7.1. And you see this part, legality rules. This is actually a phrasing taken from the ADA spec. So this is legal if, and then all of the clauses below, or all of the sentences below, are also numbered. So this is 7.1 first sentence, 7.1 second sentence, 7.1 third sentence. And we can address each and every of them. And this allows us to later consume that using our tooling, because that's what we did. So we wrote that Rust specification and then traced it to all the tests that the Rust compiler has to figure out what the test suite is actually covering. And there's something that's interesting about the Rust compiler. Safety has a lot of interest in actually behavioral descriptions. How does the tool behave? How does my software behave? If I do A, what is the effect? And one of the things you note in all of those test names is Rust calls its tests UI tests. So the massive part of the Rust test suite is actually not unit tests. It is tests that use the compiler through its front end and even go as far as testing of, okay, I put something in here that should trigger a compiler error, and it will actually test whether the compiler error comes back down to the actual error output. So the test suite of the Rust compiler is very specific to the version of the Rust compiler it's shipping with. Process-wise, this is a really, 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 really boring task. The Rust compiler ships with 10,000s of tests, and mapping each and every of them is better done a couple of hours at a time. If you force people to do this week after week, they'll be very frustrated very fast. But this was a ton of manual labor together with re-engineering the Rust specification. And these are two Sphinx plugins. So the first one is the specification numbering plugin, and then we have one that does this tracing. So you can see there's a little green button on the top. This also gives us the information of how many tests in the Ferrocene language specification we have actually accounted for, or how many of the requirements, sorry, not the tests. The other thing that's crucial about this, and I mentioned this before, this becomes part of testing. This is something that we got from the Rust compiler. There's only release builds, nothing else. That's a pretty aggressive notion on how the Rust compiler is being built. So there's only one build process, and it goes from setting up a build environment, doing all the tests, building all the documentation, checking all the traceability info, finishing the build, and actually uploading the artifacts somewhere on S3. The Rust compilers and also Ferrocene's release process is everything needs to be always green. Only artifacts that have tested completely green are even considered to allow to be ever published. Get back into one of those details later. Then it's uploaded to an artifact host. And when Rust releases, for example, something like 176, or we release something like 176, the only thing we do is we put a label in our artifact storage where we're saying, by the way, the release that was built 2 hours ago, that's 176. And that allows us to constantly re-ingest upstream. So we have all this set up, so we can always see if we can release the Rust compiler given the changes that came from upstream. And this is completely automated. So every night we do a merge of upstream. All of these have worked. Sometimes they fail. And I also see we do a lot of automation on GitHub itself. So all of these labels are given by our build automation. So let's talk about this build automation, because this is really crucial, and that was the biggest sticking point in the whole qualification. Like up to now, I've only talked about, well, Sphinx is really usable for like open source tools are really usable for the things that we do, and you can do requirements tracing in Sphinx. I think it's interesting to see, but it's let's say like just do the legwork kind of stuff. So what we're using here is this, what I said, borders in G, or what's generally nowadays called merge trains. So what do merge trains do? Merge trains maintain a queue of pull requests that are ready to be merged. So they have been reviewed. And then it serializes them for testing so that only one of the changes runs at a time. And all of those operations are completely automated. So the whole, how do we merge something is not done by clicking a button on GitHub. It's actually machinery running in the background. So it does all of the important bookkeeping. So for example, tracking who has reviewed and who has authored a change. And then it signals back on a status change. So to show you what this looks like, instead of clicking the merge button and then running all tests, what it does instead is Pietro leaves a comment here, balls merge. Then there's our Ferrocene bot that will put this in the queue, run those tests. Some points say, oh, okay, all builds succeeded, and then do the merge here. What it does in the process, you may see that it deletes something called automation backport, something in, this has been a backport change. So what BOS does, it does actually not merge things into the mainline. It forks the mainline, puts all changes on top, tests them, and if they test green, then it brings them into the mainline. Coming back to the idea of, we want everything to be everything on the main line to pass all tests. So we only merge if we actually passed all tests. That also means we do visible merges. A lot of people care about clean build history, about clean Git history, where no merges are visible. We actually want to see when merges happened and who asked for them and who signed them off. And you can also see that Boris, for example, edits all of these changes. So here we have a merge of two different changes, 1306 and 1307. And the first one has been reviewed by Pietro Albini and authored by Vekril, the author of Rust Analyzer. And the other one has been reviewed by Vekril and authored by Pietro Albini. So we have a good tracking on who actually signed off on what directly in our repository as well. We also use all kinds of Git features, like, for example, co-author tags and all of these kind of things. Like, once you're automating, why not automate these things as well? So now I've said something in between that was it serializes builds, and that's actually crucial. So one of the things we have is we only ever run one of those at a time. So only ever one thing is currently being tested to go into the main line. The reason is the following. If you do two tests in one at the same time, so you test one change and you test the other, both of them could actually completely test okay, but they could contradict each other. So if you merge the first and you merge the second, your mainline is suddenly broken. Mainline feature X plus Y is actually broken. So what it does is if the tests for feature X are running, nothing else is allowed to run in the build queue. Everything else has to wait. When those tested green, gets reforked, and then the next change will be added on top, and so on, so forth. So there's a number of ways on how to optimize that, but the general thing holds true. There's only one candidate for merges into the mainline allowed to be running at all times. You can still do pre-testing and so on and so forth. The goal here is having a straightforward path to improvement. So once all of these process things are out of the way, our goal to improve our path to improving quality is only based on the artifact. So we can do more and improve testing, other testing methodologies, and all of these kind of things. But the basis, the fundamental basis for this is regressions in any kind of quality. So things breaking are really, really hard to get in. The better your test suite, the harder it is to get regressions in. Things that are not tested, obviously you can get regressions in. And for that reason, we consider our qualification material and the tracing part of the software part of the test. It is never allowed to break. So we maintain forward all of these kind of things. So Ferrocene has for a safety product, a surprising lot of forward drift, as I would say. Okay, so those are the interesting, crucial bits about Ferrocene, and if you're ever interested, send me an email. I want to share a couple of experiences out of there, like coming back to the question of qualifying open source software, because that discussion is often had a little bit in the fundamentals. It's like you can never qualify open source software because, or all open source software is qualifiable because, things like that. As always, it's a little bit in between. Typical engineering answer, it depends. So our experience with open source tools in safety, yes, very usable. We never had a problem using Sphinx, Sixdoor, CargoDist. They are core to the speed of our delivery. Particularly the ability to modify and contribute to our tooling by ourselves at our own time scales and timelines has been very useful to us as a small organization. The maintainers have been very receptive, but for example, we have been running on a Sphinx branch for quite a while because repeatable builds for Sphinx, which is needed for our signing process, there were one or two things where Sphinx builds were not deterministic. So for half a year, we ran on a fork until they actually did a release. But that doesn't bother us. It was discussed that this is a desirable thing for upstream, so we change our things when Sphinx actually releases the thing. It is still very important to evaluate that very critically. We evaluated multiple weeks on which tools to use. And the other thing is adopt minimally. You've seen this slide of 6 major tools that we're using, and those are the tools that we're interacting with, because that makes the contributions actually worthwhile and durable. If we had a tool suite of 35 tools, I don't know what we'd be doing all day. And the other question is open source processes and safety. And our experience there is that things have changed. A lot of this mental model of open source is kind of messy. However, we found that many open source projects nowadays have processes that rival company internal processes. And my reading, also being part of leadership of one of such projects, it happens to be the one I'm talking about, those exist out of necessity. Keeping quality up while moving fast and getting a lot of contributions from the outside while the earth is turning. The Rust compiler is built 24/7 around the globe while moving fast. This is a hard problem. You need those processes to even get somewhere without breaking all the time. And why is that important? It has been quite useful for us that we have not diverged from these upstream processes, but actually done the work of describing them to TÜV and saying, hey, it's actually interesting that we keep close to them. And this is our mitigations for example, gaps in these processes, and dealing with them as such. Like, where could faults be introduced in upstream? How do we make sure that we are aware of subtle issues that could happen upstream? How do we make sure that they don't infect our flow system? However, we found that assessors were very receptive for this, depending on how good the processes of the upstream are. So our conclusion is actually open source is very usable in these kind of systems. The difficulty level could differ depending on the project. The other thing is we found that open source products in safety, it's a new niche, but it's a growing niche. And I'm pretty positive on the outlook for all of these kind of things. Particularly customers or users appreciate the ability to integrate the product however they want under well-understood licensing, Apache 201 MIT, or just pre-built, or just get pre-built software. They've got the choice. The second thing, and this has been a pretty new thing coming up in the last weeks, there's actually a big problem that research or, for example, R&D departments have nothing to look at in safety. Like, we wrote our safety manual completely from, okay, what does a safety manual actually look like? And that has been really weird to us because a lot of people that work at Ferrous, including me, have, for example, learned really industrial grade compiler engineering by just looking at open source compilers. So just the ability of having something accessible is really useful. So now we got a small flock gathering around, oh, what does a safety manual look like? Oh, well, we could actually go to the Ferrocene safety manual and just have a look at that. And that's been a little bit interesting for us. The biggest gap for customers, and I think I'm not telling you any news, is they want committed support and service level agreements. That's the most important thing. What do I do if it breaks? Who can I yell at? And that's often the Rust project, for example. Even if there's the Rust Foundation, the Rust project is separate from the Rust Foundation and is not a legal entity. Cannot get into any service level agreements. And the other nice thing is openly available documentation allows products to easily refer to each other. You can refer to, hey, by the way, I would like to deploy Rust in this way because this is how Ferrocene configures Rust, and you can do this. Another thing was we had a very good experience with automation and accepting us of common platforms. We had absolutely no issues to get our build platform, GitHub Enterprise, and Circle CI through our assessment. Interestingly, it was actually recommended to us to do that. So I know that a couple of years ago, there was still some hesitance there. For us, the feedback from the assessors was, hey, you're a 15-person company back then. Please do not run your own infrastructure because the security posture of someone like GitHub is they have a security team of just the sizes that you are or bigger. The good thing about running very straightforward and easy to follow processes is they automate very well. So implementing those in software was worth every moment. So all of that complexity that I described to you about like build scheduling and all of that kind of thing is really worth every moment because from the developer side, it's, can you please merge this PR or call me back later if it actually broke is really, really useful. We rarely run into platform limitations because we use simple processes. If we do, there's usually workarounds by, for example, using the GitHub API. So having some people that are good at scripting APIs is actually quite useful. And for that reason, and that is also something I got out of the Rust project, is there's automation should be started immediately, not even as soon as possible, immediately. The other thing is implementing automation is also a good anti-bike shedding tool of what the process should be. It is currently what the automation does. And changes are welcome, but it is really, really good to, at some areas, just have those things glued into software because that, on the one hand, it's always hard to step off what the software does. So we do have escape hatches, for example, for if GitHub goes down. But in the long run, it's also very easy for onboarding. If you tell people, hey, by the way, this is the process you want to trigger. For now, you don't need to exactly know what it does. Figure it out if it breaks. Yeah, so thank you. So in any case, I apologize. I said I had left the advertising slides off. So if you have any kind of questions around Ferrocene, please get in touch with me. Yeah, I'd be happy to have all of your questions in the Q&A here. So I have two questions here in the Q&A already, and I'm just going to start answering them top to bottom. Let me just quickly. So the first question I see here is by Daniel Weingartner. In case you get new upstream tests, do you make a manual reference to your requirements language definition? In this case, how does the manual intervention process work? I would like to actually just show you that thing in detail because it's rather simple. Let me just check out. This is my browser window. So here we go. So here's the traceability matrix and the report that you're seeing and that I've shown in the slides. So the important thing here is, so these are all the FLS coverings. So if FLS stands for Ferrocene language specification. This is the total of things that need to be linked in the specification and the amount that we currently have linked. So what we see if, for example, a test gets added in upstream, we'll see the number drop because it says, hey, there's an unaccounted for test in your test suite. And then it's a manual process and this number needs to be 100% only upon a proper release. One of the reasons why we allow the drop-off here is the test suite of the Rust project is getting massively refactored all the time, and tests are added all the time. Any new thing needs to add new tests. So it would be, so we'll be allowing those to, for example, pile up for 5 days, and then we're doing a run of test mapping. And how does the test mapping actually look like? This is one of the places where we do actually annotate the compiler source. And let me just check if I can find one quickly. Sorry. Here, for example, here's a test for tuple types. And here's a number of annotations that we have added, which is, okay, what does this test, which parts of the specification does this test test? Tests tuple expressions, tuple patterns, tuple types, type aliases, because here's a type alias used. Why is this at the end of the file? That merges well. So if this test is being edited, this remains. Because it's something that we add. If we had it as a header, that would immediately be a conflict. Otherwise, it's a change. The thing why we can do this is because tests never fundamentally change in Rust. If the test is added, but it may be, for example, changed at some point if, for example, a certain feature of the compiler is now being stabilized, and that was a test for a nightly feature or something like that. So long story short, yes, this is manual, but we can see the changes and we see the drop-off in quality if we're not accounting for them. Yeah. Yeah, Florian, I got a follow-up question from Florian Bartzels. How do you deal with test cases for experimental nightly features with Rust? We run the whole Rust compiler test suite. Nightly features are just not activated in our release builds as they are with the common Rust compiler. The reasoning here is the Rust compiler's test suite has an advantage and a disadvantage. And that being that it is not a full conformance test suite in the sense of a Rust compiler, a legal Rust compiler must behave like this. It is, however, a very good description on how the current Rust compiler behaves, and current being the current patch set. But because of the processes that I described, we can also be sure that it has completely tested upstream. So if we see one of the tests breaking, and that's one of the reasons why we also run all of the nightly tests, if a nightly test runs through in upstream and it breaks on our side, there's something wrong. And we move towards breakage as fast as possible. We want to see any kind of divergence somewhere. Okay. Another question from Florian. When creating the requirements, how did you know that you're done if requirements are missing, and which ones? Well, that was the big question that TÜV asked us, like, how do you convince us that your specification is covering? And that's the reason why the specification was half of the project's work. One of that part was that TÜV actually read the specification, read all other sources, including the RFCs, parts of that. So that was quite a substantial part of that work. So one thing that was saving for us was we do employ the people who write, for example, the Rust Analyzer IDE, so they know about even niche features in the compiler. So just having the amount of knowledge in the organization is really, really hard. And many people in the Rust project were quite approachable about, hey, does this cover all of the aspects of this topic? The other thing that's kind of saving is Rust is not as complex as something like C++. It is actually, in its principles, a relatively simple language with a lot of fluff around it. The experience complexity that a lot of people have is that some of the concepts in Rust are genuinely new. That's perceived as more complexity. Because, well, this whole ownership borrowing thing, that's not in my Java or something like that. But the description of ownership and borrowing is actually, the rules around it are actually quite short. They're just not intuitive to someone who has never programmed in such systems. From a specification standpoint, the Rust specification is relatively small. And as I said, the biggest problem were omissions. Where can we omit? And we need to be very careful about this. So for example, the Rust compiler has compiler plugins, custom deriveds, they're called. So they're essentially a form of macros that ship as a library. And one of the problems there is, from a perspective of a tool qualification, we have checked this. Yes, this interface works all right. It is the obligation of the user, though, to make sure that the generated code is never faulty because they're plugging in the plugin. So we have a number of ways where we actually don't need to cover things. We don't need to describe the borrow checker. The only thing we need to prove is that the borrow checker does not have substantial holes that we cannot document, because those the users could run into. Next question, Burak Yüksel. Have you accomplished any Dell level with any aviation project until now under DO-178? And if yes, what level was it? No, but working on it. Feel free to get in touch. We have a couple of details there that I cannot publicly speak about, but can be open about, more out of press reasons. By and large, though, we did have the DO-178 in mind, particularly when we said we're going to go the full requirements-based approach within the project. And we have, and we're currently covering some of the gaps that we still have there. The reason why we have ISO 262 and IEC 61508 is the method that we use leans towards both of those. And this was actually done as a customer project. And for ISO 26262, we had a deadline. And we reached that one. Next question is timeframe for any DO-178 certification. The problem with DO-178 certifications is, in contrast to automotive, automotive has the habit of, you can go to TÜV and say, hey, can I get a tool qualification? The problem in avionics is, so essentially, you can say, I would like to build tools for an imaginary market of using Rust in ISO 26262, which was definitely the case when we started the project. We were aware of no automotive projects that actually wanted to go into certification. This is possible. In avionics, you always need to certify for a project because there's so few assets available, they won't deal with anyone. We currently have work ongoing. We hope that we'll do the first certification by end of next year. However, we're committed to getting all of the activities ready if a project wants to finish sooner. This needs to be project driven. That's why there's so many things that are essentially certification ready. And that's what we're currently working towards. Yeah. Is there a test strategy in between requirements and implementation of tests? I don't know if I fully understand the question. Maybe you could unmute and ask something. It's been Finn Hahn.
Hello, hello, can you hear me?
Yes.
Perfect. Like the question is, like you have the requirements, and then based on that, you can derive valid and invalid inputs. Like so that's so I have the requirements, and then I build on top the test strategy. So okay, this is the range of inputs I can give. This is outside of this range, and like such form of test strategy. Is there something in between the requirements and the implementation?
So the test strategy here is set by the project again. So it really depends on what the requirement is. So the thing with Rust is Rust wants to have a lot of things, particularly things that are unsafe, to be illegal, and that informs the testing strategy. Let me see if I find a test here. So most of the tests of Rust actually go when we're testing. This is why we chip the language of illegality. Sorry, there's the Zoom thing in front of it. So the general strategy that Rust has is it has compile pass and compile fail tests. Compile pass is this is a legal Rust program and it should behave like this, which is most of it similar to a unit test. This is a so-called fail test where we say this is not legal here, and it comes with a list of annotations inside that actually says this is how the compiler behaves, like this is the error that it's giving. And there's a number of test strategies within the Rust compiler already to deal with all kinds of other failure modes that the Rust compiler could run into. In general, the Rust compiler is not allowed to crash. It must always quit with an error. So we mainly rely on the testing strategies of the Rust project already. One thing that we have added is a testing strategy around command line arguments because the Rust project doesn't have them. So yes, depending on what we're currently looking at, the testing strategies need to be changed or be informed by we're looking at one of the things that we're looking at next is actually test coverage and coverage tooling. The Rust compiler has built-in coverage. And the question is, what is an appropriate test for coverage tooling? Hope that answers your question.
Yes, thank you very much.
So, Donna, 3 questions. You talked about the Rust specification that your team created. 3 questions. Would you say that's something like this is something like a Misra for Rust? No, it is absolutely not. It is a description how the current Rust compiler, rustc, is behaving. It is also bound to the current Rust compiler version. If so, are you going to share this with the Misra committee as an open source contribution? Oh, well, no, but I'm happy if they look at it. If the specification you refer to is not in the direction of a Misra rule set for Rust, what exactly is it? The specification is really just, we describe how the compiler behaves and what it accepts and whatnot. This does not in any way collide with a Misra rule set. By the way, I know that Misra is talking about or is being approached about Rust, and I'm very positive to coding guidelines about Rust. Like even if I'm saying, hey, here's a full, like we have got the whole compiler qualified, and this is really useful, like the whole language surface. that still doesn't mean that there's something like good practice or something like that. So a Misra Rust would probably be less focused on this is how you code Rust safely, but much more, for example, things like how do you review unsafe code? The document for unsafe code reviewing. Every organization has one internally, and would be useful if we had a good one that is out there agreed on how we deal with unsafe code, what the procedures around these things are. So Rust has an unsafe subset of the language, and so I do see a lot of space for a Misra Rust, just to be clear. The next one, where do you see the strengths of Rust against those positions that say re-implementing everything that is on C or C++ is an insurmountable task? And how does Rust help in other cases of safety not related to memory only, but also logic errors, runtime errors? So first question, I always see like re-implementing everything that is in C and C++ as an insurmountable task. Yes, but that's a problem that we've dealt with the implementation of any new programming language in all spaces. I think it's also a useful position to have. Something that is safely implemented in C and that has been well vetted can sometimes just be safer than something that is quickly written in Rust. So this is actually something that the first 3 years of my company, when the Rust environment was not so well formed, did actually do a lot of consulting on, hey, and we did answer some of the consulting requests, but we don't see that you currently should adopt Rust, because when the answer to we have no problems, when the answer to do you have problems with your C code base is no, then maybe that's not a good moment for Rust. However, we have a lot of people that do have issues with their C code base. And then the question is, okay, do we fix them, or is there the door open to start afresh? And that has always been the policy of the Rust project. I know Twitter disagrees and we wants to rewrite everything in Rust. As ex-lead of the community team, I can competently say our position was always to talk to people that have actual issues and need a solution, because that's where you can get a new tool in. And also, as someone who's also owning a company, I've spoken to quite a lot of companies that did the big rewrite in another language for absolutely no reason at all, because they wanted Scala and their CDO wanted Scala and just paid a couple of millions and ended up with a product that they didn't end up using and threw away. So yeah, I think this discussion should be complexified, but the results, but we should be open to all results. Second question, where does Rust actually help? Rust does not only have memory safety, it has things like algebraic data types. So you can say, hey, here, one function returns an error or a success, and you need to check whether it returns an error or a success. So there's no way past checking these kinds of things. So Rust has quite a few features that lean towards functional safety that I cannot go into detail in this short minute. But my personal position is, I would love if we actually stopped talking about memory safety for a while and talked about the other features of the language. So moving on, Andrew Taidu. You mentioned that you could qualify any version, but that you also found some bugs in our bare metal targets. So how does it work if someone chooses a version 1NN, but 1NN has bugs for customers target? We do backports. So if we find a bug in a future version and we feel it's appropriate to do backports or other kinds of mitigations, we do assist in that. That's part of our service. The question is always with backports, depending on how large the backport is to fix such a bug, maybe there's more, like maybe upgrading to a new version is more appropriate, or just avoiding the bug can also be, like, if I need to ship a 10,000 line change to the compiler, I'd rather ship an identification tool to the customer that actually figures out whether they actually hit the bug or not. So one of the examples I can give is there's a linker flag for GCC that for the GNU linker that avoids a certain hardware error in a certain ARM Cortex-R that the Rust project wasn't aware of and hadn't added. The thing is, if you're not deploying on those specific runs, production runs of an Cortex-R, well, then you don't need this. So the assessment there is part of what we do. Next question. Qualified compiler is only part of a certified system, but then there's also parts of the problem, other parts of the problem, standard library, code coverage. What are Ferrous recommendations for people who need qualified solutions for those parts of the toolchain too? We're currently working on those. So we've only reached the first item there. It was very important, I think, as a signal that we do reach qualification. Can also share the 168 version. Qualified version will probably never be used in production anywhere because all of those people will move to the 176 that we're currently qualifying. Yeah, all of those gaps need closing. One thing I can say though with test coverage, most C-based coverage approaches for Rust do not work, particularly anything that rewrites source code. Rust source code cannot be rewritten easily. So that needs to be done through other approaches. I know that Toyota has sent a lot of fixes to MCDC tests, MCDC being built into the GCC compiler and LLVM. And we're currently working at attaching those to the Rust compiler, qualifying it, and all of these kind of things. Yeah. Andrew, again, did you spot any places in rustc that were bugs, but their current tests lacking and didn't exercise that bug? How are those documented and shared upstreams? How does that affect quality of the version you found bugs in? Just document the user, don't use code patterns like this. So there are obviously bugs in rustc, and we have a known issue list. Many of them are very niche. We have found quite a few bugs when we actually started doing bare metal testing because that was never tested before. All of those just get fixed upstream. So we contribute all of those. So that was the slide on our trophy list of like most highlighted bugs that we found. Yeah, just documenting to the user, don't use code patterns such as this, is a last resort, I have to say. However, making them aware of that issue is really useful. You may have seen, and there's things that are just fundamental logic issues. You may have seen recently there was a thing called CVERS, which was highlighting a bug in Rust's type system that is really, really hard to trigger. You need to jump through a lot of hoops. And if I meet a safety critical engineer ever going very deep down into the type system and to trigger a very niche bug to break memory safety, I think I have a couple of words for them. Really depends on the bug. Most of the time, that's what I mean with correctness is the value of the Rust project. Getting a fix upstream is really, really easy. There's a lot of, like, the change process of Rust is pretty hard when you're talking about the language surface. But bugs that are obviously bugs get fixed within 24 hours or something like that, or depending on how long, like actually figuring out the validation works. So for us, actually, the best way is to upstream it, inform our customer, and see if they need a fix, and then maybe backport it. Okay. That was all the questions.
Yes.
Last one.
Thank you, Florian, for the very engaging talk, and thank you all for participating and posting your questions. Hope this is very informative. And if you would like to know more events that ELISA hosts, please check our website at elisa.tech. And actually, our next webinar is going to be on making Linux fly towards certified Linux kernel. Check it out and register to attend on May 22nd. Thank you all.
Thank you.